If you haven't already heard, our solar system is currently host to a strange and intriguing visitor. Comet 3I Atlas burst onto the astronomical scene in early July 2025, when it was first identified by the NASA-funded Atlas Survey Telescope, or Asteroid Terrestrial Impact Last Alert System, operating in Rio Hurtado, Chile. Since then, scientists across the globe have assembled to collect every scrap of information they can get about this elusive entity. This has led to a flurry of articles, alerts, papers, and controversies about the first interstellar object to enter our cosmic backyard in 6 years. But amid this media frenzy, what have we actually learned? What information about this comet is true, and what lies in the realms of science fiction? I'm your host, and you're watching Stellify Science. Join me in this video as I give you a much-needed update on 3I Atlas, piercing through the noise and getting to the heart of what makes this visitor so special, just in time for its October 30th perihelion. If nothing else, the buzz around this comet proves how dynamic the world of science research can be. When I made my first video about 3I Atlas back in July, there were only around 4 published research papers naming it. Now, as of September, there are nearly 70. That represents a huge number of new discoveries, verifications, and boosts in our collective knowledge about this object. But before I dive into the newest findings, let's do a quick recap of where we left off. In my previous video, I discussed the initial discovery of Comet 3I Atlas, named for its status as the third interstellar object to visit our solar system, and the Atlas Survey Telescope that identified it. I compared this comet to the famed Oumuamua, which made its way through our solar system in 2017, and Borisov, which was discovered in 2019. In contrast to its 2 interstellar predecessors, 3I Atlas is thought to be much faster. Traveling at a whopping speed of 58 km per second, it is also older, with estimates that it is somewhere between 3 and 11 billion years old. That was a speedy summary, so you should definitely check out my first video. But since 3I Atlas made its debut on the channel, we have learned a lot more about it, thanks to countless hours of observation and measurements from astronomy facilities across the globe. So, what's the latest information to come from this researching spree? With the worldwide recognition that 3I Atlas has attracted since its discovery, it has managed to turn the heads of 2 very prestigious telescopes. It's famously difficult to schedule observation time with NASA's Hubble Space Telescope, with scientists having to submit proposals months in advance to argue their case for every minute of the telescope's time. But luckily for 3I Atlas, Hubble always reserves some time for so-called targets of opportunity, things that need to be observed before they move out of our reach, giving this unexpected interstellar visitor a free pass to skip the queue. And it was definitely worth it. Hubble captured an image of 3I Atlas on July 21st, when it was 446 million kilometers from Earth. You can get a sense of how fast the comet is traveling from the streaky stars in the background, and see the teardrop shape of the dust coming off its icy nucleus. These observations also allowed Hubble scientists to make estimates for the size of 3I Atlas's nucleus, measuring it between 440 minutes and 5.6 kilometers in diameter. That makes it a lot smaller than we originally thought, since original estimates of its size assumed that the comet's reflectance was coming entirely from the nucleus, not the coma. Now that the dust is cleared, we can see things in finer detail, and future observations may be able to pin down these measurements even more. The other major player that has turned its attention to 3I Atlas is the James Webb Space Telescope. On August 6th, scientists used JWST's near-infrared spectrograph in an attempt to determine the composition of this comet, in a study led by astrochemist Dr. Martin Cordner. They found a complex coma morphology, suggesting a range of different outgassing patterns depending on the elements and compounds being released. It seemed that carbon monoxide and carbon dioxide were sublimating more at this stage than water. But this is likely to change as the comet gets closer to the sun. While comet tails usually point away from the sun, the researchers found a surprising amount of dust emanating from the comet in the direction of the sun. This was caused by the dust grains fragmenting as they move further from the nucleus, and in turn, reflecting more light. This process might be exacerbated by gas production, as excessive carbon dioxide production could actually be launching the dust further away from the nucleus. Pretty dramatic for a feature that appears to us as nothing more than a hazy glow. Hubble and James Webb are not the only NASA telescopes getting in on the 3i Atlas fun. The Transiting Exoplanet Survey Satellite, affectionately known as TESS, has spent more than 7 years conducting an all-sky survey to discover exoplanets orbiting around nearby bright stars. It uses 4 identical wide-field cameras to map the sky in 90 by 24 degree strips and has already discovered thousands of planetary candidates. But as it turns out, TESS isn't just good at detecting exoplanets, but smaller objects too. Objects like comets. In my previous video, I mentioned that the first official discovery of 3i Atlas was actually predated by observations going back to June 14th. However, astronomers working with NASA's TESS mission realized that they had observational data for this comet, dated all the way back to May. The comet was captured by TESS from May 7th to June 2nd and was made visible in composite deep stack images. With this new data, astronomers had the chance to verify the earlier measurements made from 3i Atlas and make some new discoveries of their own. In a paper published on September 11th, Adina Feinstein, John Noonan, and Daryl Seligman used data from TESS to measure the brightness of 3i Atlas. They found that the average visual magnitude recorded by one of the TESS detectors was in line with previous estimates made by other astronomers using the same data. But the comet was about to defy expectations in another way. Between May 7th and June 2nd, the distance between 3i Atlas and the TESS spacecraft decreased by 0.9 AU. From this change alone, the authors expected the object to get brighter, since it would be closer to the sun and could reflect more of its light. They calculated that the comet's flux, or the amount of energy received from it, would increase by a factor of 1.5, corresponding to a magnitude of 20.5. But the object got much brighter than that. Its magnitude increased to 19.28. This shocking surge in brightness was the result of 3i Atlas, increasing its flux by a factor of 5, not 1.5. Observations with the TRAPPIST. North and south telescopes reported similar brightness values, confirming there was no miscalculation. With such a huge amount of energy radiating from this object, 3i Atlas is far more active than we originally thought, and may have been active for a long time. Combining their magnitude values with the Hubble estimates for nucleus size, the researchers found that 3i Atlas may have been active when it was still a whopping 6 astronomical units away from the sun. That's near the outer limits of where comets usually start outgassing, suggesting that 3i Atlas might have been releasing something more exotic and hypervolatile at this time, like nitrogen or hydrogen. In my previous video, I said that 3i Atlas had a flatter light curve than Oumuamua, which suggests that it reflects light more evenly across its surface. Feinstein and her colleagues came to a similar conclusion when they tried to extract a light curve for this comet using the TESS data. In fact, they struggled to find any patterns in the light curve at all, so they couldn't conclusively identify the comet's rotation period. They did identify some periodic signals, one every 29 hours and another every 16 hours, But the data was noisy, and tests may not have been sensitive enough to measure this kind of parameter for a faint object like 3I Atlas. Luckily, other studies using specialized ground-based telescopes agree with the 16-hour spin period, so we can be more confident of the comet's shape and how it rotates. I've only covered space telescope discoveries so far, but discoveries about 3I Atlas have been made by telescopes back on Earth too. On August 27th, researchers working with the Gemini South Telescope in Chile used the Gemini Multi-Object Spectrograph to visualize 3I Atlas in multicolor. Amazingly, the images captured in this session showed not just the coma around the comet's nucleus, but its tail. The tail was measured to span about 1/120th of a degree in the sky, which is significantly longer than it appeared in previous images using the Gemini North Telescope back in July. This is further proof that 3I Atlas is becoming more active as it approaches perihelion and hints at exciting developments to come. Who knows how much more the tail will grow before the comet reaches its perihelion on October 30th. The August session also collected the spectrum for 3I Atlas. In this recording, you can watch the moment when Bin Yang, assistant professor at Diego Portales University, identified an emission feature in the CN band for the comet, proving that it was releasing cyanide molecules. This happens when water sublimates upon exposure to sunlight, releasing hydrogen cyanide from the comet, which is then broken apart by sunlight into its constituent elements. We often start to see this when a comet is between 2.5 and 3 astronomical units from the Sun, which is exactly where 3I Atlas now finds itself. Other observatories have affirmed this finding, as the once-weak CN signature is steadily strengthening over time. A paper published at the beginning of September inferred that the comet was releasing 800 sextillion, or 8^10^23, cyanide molecules per second when it was just over 3 AU from the Sun, which is actually on the lower end of the scale for many comets in our solar system. By measuring the ratio of dicarbon, C2, to cyanide in the coma, the authors placed 3I Atlas as one of the most carbon chain depleted comets we know of. But what does that mean? Carbon chain depletion occurs when a comet's coma or tail is lacking in longer chain carbon molecules like C2, dicarbon, or C3, tricarbon. This feature is used to classify comets found across the solar system and is thought to reflect the conditions in which they were first formed. Using an upper limit for the comet's C2 production, scientists concluded that 3I Atlas produces less than 0.09 C2 molecules for every CN molecule, and so it is carbon chain depleted. Interestingly, Borisov also shared this feature, so this may point to a pattern in the composition of these comets. However, it's important to note that the interstellar sample size is still very small, so we should try to avoid overgeneralizing. Either way, we should keep an eye on 3I Atlas as it approaches our Sun. As dicarbon production could rise, the comet could start outgassing more H2O, or something even more dramatic could happen. As astronomer and comet expert Karen Meach has said, these comets are really very fragile, dirty snowballs, and can often break apart. If that happens, we could see a renewed bout of emissions as the break exposes untouched water ice to the Sun's radiation. In recent days, researchers have analyzed not only how 3I Atlas emits light, but how it polarizes light. On September 5th, a paper was published by Zuri Gray and colleagues presenting the first ever polarimetric observations of 3I Atlas, and by extension, the second ever observations of this kind for an interstellar object, the first being Borisov. Polarimetry is used specifically to probe the physical properties of space objects, like the size of their dust grains, the structure of their surface regolith, and the shape of their coma, in a way that cannot easily be done with other techniques. Gray and her colleagues used data from telescopes across Chile the Canary Islands, and Bulgaria. They managed to discover something about 3I Atlas that set it apart from any other interstellar object, asteroid, or comet we've seen before. They found that 3I Atlas has an exceptionally deep and narrow negative polarization branch. That may not sound like much, but it means that 3I Atlas is scattering light in such a way that has never been seen before for any other comet or asteroid in our solar system. This behavior sets it apart from even Borisov, which showed positive polarization of light, and could place it in a distinct class of small planetary bodies that we know next to nothing about. To give some more context, particles in and around space objects, like dust or gas, can cause incoming light to scatter in specific directions. This is known as light polarization, and it can be measured by telescopes here on Earth. Experts look at the scattering plane, which is the line formed when looking from the observer to the comet to the sun, and record whether the direction of polarization is perpendicular to the scattering plane, positive, or parallel to the scattering plane, negative. The deep and narrow negative polarization of light from 3I Atlas means that the light is being strongly polarized in a very localized parallel direction to the scattering plane. This pattern is somewhat comparable to some trans-Neptunian objects and centaurs, but further research is needed to pin down exactly why this might be the case. If you thought the newsworthy observations of 3I Atlas were reserved for academics, you'd be wrong. Science really is for everyone, and this next discovery proves why. From September 7th to 8th, parts of the globe were treated to a stunning lunar eclipse, or blood moon, as it passed through the Earth's shadow. Naturally, this was a great opportunity for amateur astronomers to dust off their telescopes and have a look. But some space enthusiasts weren't just looking at the moon. Michael Yeager and Gerald Riemann were taking photos of the night sky over Namibia when they noticed our friend 3I Atlas, colored with a surprising yet beautiful green hue. Now, this finding hasn't been verified by scientists at the time of writing, but comets in our solar system can turn green when they begin to release diatomic carbon, C2, which gets energized by sunlight and fluoresces near 518 nanometers. This behavior may be normal for other comets in our solar system, but as you'll remember, 3I Atlas was recently found to be highly carbon-depleted, so it shouldn't really have much C2 to fluoresce. Maybe it's a sign that C2 production is ramped up in recent days, but again, we'll need further research to confirm or deny this theory. Whatever the case, it's a beautiful image, and this latest mystery has captured the attention of amateur astronomers and scientists alike. At this point in the video, there is still one major area of development in the news surrounding 3I Atlas that we haven't touched on yet, but it's one I'm sure you've heard about. The name Avi Loeb pops up a lot in the media coverage of this comet, and he has a lot to say about where or who it came from. Avi Loeb is a renowned astrophysicist and Harvard professor who has stirred up his fair share of controversy throughout his career. His most recent obsession with 3I Atlas has received mixed responses from his fellow scientists and the wider public. Back in July, Loeb was already publishing his comments on the discovery of 3I Atlas. And at first, it all seemed pretty astrophysical. One of the main points from this paper, and from Loeb, is that 3I Atlas is too large to be an asteroid. Early estimates of the comet's radius put it at around 10 kilometers. Loeb pointed out that this would give the comet a far greater mass than we would have thought possible. Given our current understanding of how much material there is in interstellar space, an object this large entering our solar system should be an extremely rare occurrence. In light of this argument, Loeb suggested that 3I Atlas may be smaller than we originally thought. But he also suggested a controversial alternative, that alien technology could be the explanation. Just days later, Loeb submitted another paper, along with 2 collaborators representing nonprofit organizations for interstellar exploration. And the title of this paper is The Interstellar Object 3I Atlas Alien Technology. While Loeb's first paper only briefly floated the idea, this follow-up placed the alien speculation front and center. In it, the authors conducted an analysis of the astrodynamics of the comet, exploring whether it could be technological and possibly hostile. They reference the dark forest resolution to the Fermi paradox. If you're not familiar, we've covered this in previous videos. But the Fermi paradox poses the question of why we haven't found aliens yet. Considering the size of the universe and the number of stars that share similarities with our sun, the dark forest idea suggests that perhaps aliens are out there, but are choosing to remain hidden, like prey would hide from a hunter. The authors stress that they are exploring this idea for educational purposes, and because it is fun to pursue, irrespective of its likely validity. So, let's see what they had to say. Firstly, in this paper, Loeb still maintains that 3I Atlas is too large to be an asteroid. As Loeb and his colleagues should know, estimates for any newly discovered object are liable to change, especially as more independent measurements are taken, and results are peer-reviewed. After all, the 10-kilometer value was estimated before we could properly measure 3I Atlas's coma, and as we now know, that coma is responsible for most of the reflectance we see. A press release from the Hubble team on August 7th said that 3I Atlas measured 5.6 kilometers across at most, but Loeb continues to use the outdated measurements in his alien hypothesis. In a Medium post on August 13th, Loeb directly mentions the Hubble images, but still bases his argument around the older estimates. The issue is not that scientists should be banned from pursuing alternative lines of research, but they should at least make sure that the research uses credible data, especially for new discoveries like 3I Atlas, where the state of our knowledge is still a constant work in progress. As for Loeb's other points, well, they've been rebutted by other scientists, particularly in 2 papers by Akm Yasinul Haque, a geoscientist working at Petronas University in Malaysia. He rebuffs Loeb's arguments for non-gravitational acceleration to achieve a non-coincidental flyby of Venus, Mars, and Jupiter by referring to the most recent trajectory data for 3I Atlas, which can be explained far better with natural dynamics than engineered maneuvers. For many of Loeb's critics, this is a lesson against jumping to conclusions. As fun as it might be to cry aliens, we should at least wait for the dust to settle on each new discovery before we start looking for whether it could be a sign of intelligent extraterrestrial life. That way, we'll be far more efficient at coordinating a response if and when the evidence truly points to an alien encounter. We've come to the end of our reunion with 3I Atlas. But as I've shown in this video, this research moves almost as fast as the comet itself, so we're by no means finished making new discoveries. On October 30th, the comet will reach perihelion around 1.4 AU from the Sun, though sadly we won't be able to see it. At the time this video is released, it will be too close to the Sun to observe, but don't panic. It will re-emerge by early December, ready for a renewed bout of in-depth analysis. Missions that may be able to observe the comet include NASA's SOHO, SphereX, and MAVEN, not to mention continued observations from Hubble, James Webb, and the Gemini Observatory, so there will be plenty more to come. As 3I Atlas takes a bow and disappears behind the solar curtain, it leaves plenty of questions for us to ponder. How will its activity change as it reaches perihelion? Will it break apart? How long has it been traveling to get here? And can we trace its elusive origin? It's a race against time to answer these questions, but astronomers are showing no signs of slowing down, and I can't wait to see what they discover next. Solving the mystery of Comet 3I Atlas is only possible by finding patterns in the data. It requires analyzing mountains of data, spotting subtle patterns, and testing ideas against the evidence. It might seem complex, but it's a skill set anyone can develop with the help from today's sponsor, Brilliant. Brilliant is an online learning platform with thousands of interactive lessons in math, science, data analysis, programming, and AI, all created by experts from Stanford, MIT, Microsoft, and Google. It gets you involved from the very beginning, then uses hands-on practice to actively build your understanding. No wonder it's 6 times more effective than passively watching lectures. They've also added a bunch of new courses like Thinking in Code, or my favorite, Probability and Chance. Each lesson is short, engaging, and designed to make daily learning a habit, so you can reach your goals faster. Are you ready to think like an astronomer and start finding your own patterns? Give Brilliant a go. Start your journey today.